Hello, my name is Marko Kleine Büning, and I want to give a short introduction of our topic, verifying equivalence properties of neural networks with ReLU activation functions. This is a joint work together with Philipp, Kern and Carsten Sinz at the KIT. First of all, I want to motivate the formal verification of neural networks. Neural networks are applied in many different fields, but they are increasingly applied in safety-critical systems, like autonomous cars or airplanes. So we have to argue about their reliability. One problem that can, for example, occur are adversarial attacks. So you have a stop sign, and then you add some noise to this picture, and then the neural network misclassifies this picture, leading, for example, to an accident. So there are many different properties you want to prove for neural networks. One is equivalence. Assuming you have a sufficiently reliable reference network, then you ask the question, is another network, is my network equivalent to this reference network? This can be applied in many different areas. For example, if you want to reduce the size of a network, if you, for example, want to deploy it onto a device, or if you have additional training data and do not want to lose all prior guarantees. So our approach aims at proving or disproving the equivalence of two feed-forward neural networks. We do this by looking at a common input space with training data, then two networks that are either equal or not, which each has then an output. So the question is, are these networks equivalent? But we do not want to argue about number of nodes or edges or anything, but we want to argue about the relation from input space to output. So first of all, we only want to argue about relevant input. So we cluster the input space. The second point is that we need to find a notion of equivalence. So we define three novel notions. And then this whole approach is encoded into an Int'l problem. And then given to a solver, in our case, Gorobi. The results can be shown in two different kind of areas. For example, on the left, you see we have an equivalence radii for different clusters, and we see the radius goes down when you increase the pruning of the network, so the size reduction. On the right, you see a counterexample, so a new data set or data point we generate, where the two networks classify a picture differently. And here you see, in my opinion, a picture of a 0, and the full NN classifies it as a 0, but the 20% prune network classifies it as a 6. So thank you for your attention, and if you have questions, comments, or are interested in this topic, please listen to the detailed talk, ask questions at the CP20 session, read our paper, and always feel free to contact us per mail.
Hello. My name is Philipp Kern, and after Marko has already given a short introduction to our topic, I'm going to continue with the detailed talk. As Marko has already said, we are concerned with equivalence of neural networks, and for that we are given two fully trained neural networks and are interested in whether they produce equivalent outputs for all relevant inputs. Ultimately, we want to encode this problem into a mixed integer linear program, or MILP for short, in which we want to maximize the violation of a given equivalence property. And in the process of the talk, we want to use this slide as an orientation, starting with the encoding of a single neural network. A feed-forward neural network, to which we restrict ourselves, can typically be ordered or into a number of layers. It computes its function by taking the inputs that are fed by the user to the neurons in the input layer, and then propagates these inputs through the layers of the neural network until the output layer. Along this path, each individual neuron computes a function first computing a linear combination of its inputs according to the weights it has learned in training, and then applying a nonlinear activation function. The most commonly used activation function is the ReLU activation function, to which we restrict ourselves. It is just 0 for all inputs less than or equal to 0, and the identity function otherwise. We can encode it into MILP by encoding this behavior as implications, and encoding these implications using the big M encoding. Given that encoding for a single neuron, we can encode the whole neural network by stacking those single neuron encodings together. With that out of the way, we can now focus on what does equivalence for neural networks mean and how can we encode these equivalence properties. But first I'm going to introduce some notation. So we are given a reference network R, as well as a testing network T, and each of them compute their outputs using the function fr and ft of some input, and we get their output vectors r bold and t bold. Because they compute functions, a natural equivalence property would be just use functional equivalence. So for all inputs in the input domain, both the reference and test network should produce the same outputs, and then we would consider them equivalent. This can be expressed in terms of a violation score by just subtracting their output vectors from each other, and if the norm of their difference is equal to 0, then we would consider them equivalent. However, in practice, this is far too restrictive. Remember that neural networks are generally trained using stochastic gradient descent. So even if we had two same network architectures and we trained them on the same training dataset, they could still produce slightly different results. And a natural relaxation of the equivalence property would be to say the two networks are equivalent if their outputs are sufficiently close to each other. So we essentially drop this 0 and replace it with some epsilon threshold to get to epsilon equivalence. However, this only makes sense for regression settings. In classification settings, the output of a neural network actually represents the probability distribution. In this example, the neural network classifies the input as belonging to the green class, as it assigns the highest output activation value to the component belonging to the green class. And in this setting, we are not really interested in the whole output distribution, but just in what is the class that the input was assigned to. And in that case, we define the networks to be equivalent if both classify the input as belonging to the same class, or more formally, if both of the networks assign their largest output value to the same component of their output vector. So in this example, the two networks would be equivalent because they assign their largest output activation both to the first component. When we put this in terms of a violation score, we look at the classification result of the testing network, which is the first component in that case, and the component in the testing network that corresponds to the classification result of the reference network. So the classification result of the reference network is the first component, the corresponding component in the testing network is also the first component. So we calculate 0.6 minus 0.6 is 0, and those two networks will also be equivalent. These networks, however, should be different, as the reference network classifies it as belonging to the first component, and the testing network classifies it as belonging to the second component. Accordingly, the classification result of the testing network is T2, while the classification result of the reference network hasn't changed. So T1 is the testing network component corresponding to it. And then we'll calculate 0.6 minus 0.3 is equal to 0.3, and thus those two networks would not be equivalent. However, we can relax this equivalence property into not only taking into consideration the top output or the classification result, but instead the k most likely classification results. So we now consider two networks Top-k-Equivalent if the reference network classifies the input as belonging to class J, and then the component Tj in the output vector of the testing network should be amongst the k highest output activations of the testing network. In terms of a violation score, we now search for the kth largest output activation in the testing network. Let's say we look for k is equal to 2, then we have T1 as the second largest output activation. Tr is the component in the testing network corresponding to the classification of the reference network. This would also be T1, and then we would calculate 0.3 minus 0.3 is equal to 0. So those two networks would be top 2 equivalent. Please note that we need a unique maximum among the output values of the reference network. because later on our solver is trying to maximize this violation score. Now, if there were two equal maximum values in the reference network's output, we could end up with a situation such that the solver picks one of these outputs amongst the reference network, such that the violation value is larger than allowed, despite one of the classification results of the reference networks being in the top k classification results of the testing network. Now that we have defined the equivalence properties, we still need to encode them into MIL, or more specifically, we need to encode their violation scores in MIL. For Top-k-Equivalence, the difficulty lies in that we need a sorted output of the reference as well as the test network to obtain the violation score. So to obtain the classification result of the reference network, we can apply a permutation matrix to the output value or the output vector of the reference network to obtain a sorted output vector. And we can ensure with these conditions that this is indeed a permutation matrix. And these conditions ensure that this is indeed properly sorted. To get the top k outputs of the testing network, we can essentially apply the same trick. And to get the output of the component of the testing network that corresponds to the classification result of the reference network, we can apply this permutation matrix to the output of the testing network to obtain TR. Now we have introduced a lot of variables. However, we don't really need all of them. Remember, we are just interested in the classification results or the top output of the reference network, so we can drop all the remaining rows. Then we are also only interested in the top k classification results of the testing network. So in our example, if k is equal to 2, we can drop the last row. And then we still need to ensure that the reference network has a unique maximum. And we do that by setting for every component that wasn't chosen as the maximum, we require the maximum to be larger than that by at least epsilon. Note that typically multiplications between variables are not allowed in MIL. However, the permutation matrices only contain of binary variables, and we can encode these multiplications as implications and are thus legally allowed to use them in MIL. The encoding of epsilon-equivalence is less complicated. We just encode the difference between the output vectors and then have to encode the norm. Because we can only exactly encode piecewise linear norms in MIL, we have chosen to encode the Manhattan as well as the Chebyshev norms. The absolute value can just be encoded using implications again, while the maximum operator can be encoded just as we've seen with the sorting for Top-k-Equivalence on the previous slide. With that out of the way, we are now left with the consideration of the input space. When we put together what we have so far, we encode the reference network, we encode the test network, and obtain their outputs on a common input. And from these outputs, we can calculate a violation score, and we maximize this violation score over all possible inputs. And if that maximum violation score is sufficiently small, we consider the networks to be equivalent. Otherwise, we can obtain the maximizing input and use it as a counterexample to the equivalence of the neural networks. If we run this optimization procedure for two neural networks trained to classify handwritten digits, this is, for example, what we obtain as a counterexample. And it clearly doesn't resemble any handwritten digit. It merely shows that two neural networks are not encouraged to learn the same concept in regions far away from training data. To mitigate this problem, we applied a hierarchical clustering approach to the training data and restricted the allowed input to clusters to a certain radius around cluster centers of training data, and are now able to generate much more meaningful counterexamples. With this notion of equivalence, we can not only ask ourselves what is the maximum violation score for that region with that radius, but another natural question is how large can we make that radius such that two neural networks are still equivalent around the cluster center. And in this case, we achieve this by actually minimizing the radius such that the solver can still find a counterexample around the cluster center. With that slide, we also concluded the theoretical part of our talk and can turn to our application, the compression of neural networks. So modern neural networks can have a very large number of parameters, which prohibits their deployment on, for example, embedded devices. So the task now is to reduce their complexity while don't losing too much performance. And two approaches to achieve that are low magnitude weight pruning, where we look at connections between neurons, and if they are associated with a low magnitude weight, we essentially set that weight to 0, meaning we remove that connection from the network. Another approach is student-teacher training, where we directly train a smaller network on the output of a larger network, instead of on the training data labels, because the output of the larger network generally has a higher entropy than training data labels. We evaluated our approach by training neural networks on a handwritten digits dataset to classify those handwritten digits given by 8 by 8 pixels. Our initial neural network had layers of 32 and 16 neurons, as well as an output layer of 10 neurons, each of these outputs corresponding to one of the digits. And then we reduced the neural networks by low magnitude weight pruning and student-teacher training. Subsequently, we applied the clustering approach to obtain the centers of the 5 most dense clusters, shown below. And in the upcoming slides, I'm going to talk about the results of the radius maximization for top-1 and top-2 equivalence for low magnitude weight pruning. So for one-hot or top-1 equivalence, we can see here in this figure, we have the number of the percentage of weights we set to 0, and on the y-axis we have the radius of the equivalence radius around the center for each of the 5 clusters. And we notice that we can that the equivalence radius is fairly stable up until 50% of pruned parameters. Later on, if we prune too many parameters, the equivalence radius deteriorates. But in between, something interesting happens. There are some difficult clusters for which the equivalence radius gets smaller, but there are also easier clusters for which the equivalence radius stays the same or even increases. For top-2 equivalence, we can see that the radius is in general larger than for top-1 equivalence, which is to be expected. But also, in some cases, we only have lower and upper bounds on the equivalence radius and no optimum value. This is because our solver timed out after 3 hours, which leads us directly to future work. So to address this issue of scalability, we can use or develop dedicated solvers for neural networks. We could also employ approximative methods, or also generate bounds on the variables that are used during the verification process directly during training of the neural networks. While we still need to work on these issues, we are nonetheless able to prove or disprove equivalence of given neural networks in relevant input spaces using epsilon, top-k, and one-hot equivalence. Thank you for your attention.